Okay, in this video I am going to go through AS level chemistry, OCR, paper 2, the 2017 paper. I'll just do half of the paper in this video and I'll do the second half in a later video. Okay, right, so the first question is about barium compounds. Barium oxide has a giant ionic lattice structure. What is meant by the term ionic bond? Well, it is the electrostatic attraction between positive ions and negative ions. Dot cross diagram now for barium oxide. Well, barium is in group 2. It's going to form Ba2 plus ions, so it loses all the electrons in the outer shell. So I'll just draw that like this. Oxygen is in group 6, got electronic structure 2,6, so it's going to form an O2 minus ion. Okay, so draw the dot cross diagram for oxygen. It's got 6 of its own electrons, the oxide ion, and it's got 2 electrons which have come from barium. So the charge on that is going to be 2 minus. Okay. Right, calculate the number of barium ions in 1.5 grams of barium oxide. Okay, so we're going to have to use the Avogadro constant for this. Now, barium oxide, the formula for barium oxide is BaO. Barium has got an atomic mass of 137.3. Oxygen, of course, is 16. So the molar mass of barium oxide is 153.3. Okay, now we need to work out the number of ions. We need to work out the number of moles of barium ions we've got. So first of all, the moles of barium oxide is going to be mass over the molar mass, 1.5 over 153.3, which gives us 9.28 times 10 to the minus 3 moles of barium oxide. And that is also going, because 1 mole of barium oxide contains 1 mole of barium ions, that is the moles of Ba2 plus ions. Okay, now we want to work the number out rather than the moles. We have to multiply by the Avogadro constant. So the number of barium 2 plus ions is equal to the moles multiplied by the Avogadro constant, 6.22 times 10 to the 23, and that gives us an answer to 3 significant figures of 5.89 times 10 to the 21 ions. So that's that question done. Right, barium chloride is soluble in water. Compare the electrical conductivities of solid and aqueous barium chloride. Right, so barium chloride solid does not conduct. Why not? Because the ions can't move. The ions are fixed in the lattice, okay, in fixed position, and they can't move about. The flow of ions is what constitutes the electric current. Right, now the aqueous solution will conduct because the ions can move. The ions are free in solution and they can move about. So that's all you need to say for that, I think. Okay, describe the use of aqueous barium chloride in quantitative analysis. Right, this is for 2 marks, so I think what you need to say here is, right, so it all based on the fact, so we've got barium chloride. Of course, the formula of barium chloride is BaCl2. Right, so you add acidified with HCl. And for 2 marks, I know that you need to explain why you need to acidify it. acidified barium chloride solution to the solution that you suspect may contain sulfate ions. Okay, and if sulfate ions are present, you will get a white precipitate of barium sulfate. I think you might as well write down the ionic equation for that. So Ba2 plus Aq plus SO4 2 minus Aq will give you barium sulfate solid. So it's a test for sulfate ions in solution. Okay, hydrated barium chloride can be crystallized from solution. Okay, hydrated barium chloride has this formula, okay, and this molar mass. And we've got to determine the value of X from that. Right, so we write down barium chloride XH2O. Right, what does this part of the formula weigh? Well, it's going to be one barium atom, which is barium's 137.3, plus 2 times 35.5 for the chlorine. That gives us 208.3. And we know that the whole thing in yellow here, that weighs 244.3. Right, so how much does this XH2O weigh? Well, that weighs 244.3, and subtract the 208.3, which gives us 36. Now we know that the MR of water, molar mass of water, is 18. So the value of X is going to be 36 over 18, which is equal to 2. So the value of X is here is 2. Right. On to barium nitride. Right, complete the electronic configuration of a nitride ion. So we know that nitrogen is 1s2, 2s2, and it's got 3 electrons in the p shell. Right, once it get a full p shell to form the nitride ion, so it gains 3 more electrons to form, so it's full up, so it's 2p6. Right, now barium nitride reacts with water, okay, to form an alkaline solution A and an alkaline gas B. Right, let's work out the formula of barium nitride first of all. So barium always forms a 2+ ion, it's in group 2. The nitride ion we've seen is N3-, so the formula of barium nitride is going to be Ba3N2. So the charge is balanced. Right, now we're going to react that with water. Right, now the alkaline solution, well, barium forms alkaline barium hydroxide, so that's what the alkaline solution is going to be. And the alkaline gas, you may be a bit puzzled by that, but you think, look, you've got nitrogen barium nitride, that's probably going to form ammonia. That's an alkaline gas, so it's probably ammonia. So NH3. Right, let's now balance that. So we need to put a 3 in front of that because we've got 3 barium atoms. Now, sorry, that's not the right formula for barium hydroxide. BaOH twice, of course. Right, now we have got 6 oxygens in that. We've got 3 lots of barium hydroxide, 6 oxygens, so we're going to need 6 waters. We need to balance the nitrogen. We need to put a 2 in front of the ammonia because we've got 2 nitrogen atoms. Let's just count up those hydrogens, make sure. Well, we've got 12 on the left. Okay, now we've got 6 in the barium hydroxides, and we've got 6 in the ammonia, so that all balances. So that is our equation. Okay, now this is looks like a rate of reaction experiment. The student was asked to carry out an experiment to determine the initial rate of reaction and was between zinc and hydrochloric acid. He plans to collect about 72 centimeters cubed of hydrogen. Okay, so we can work out the moles of that because we know the molar mass is 24,000 centimeters cubed. Okay, and it's going to use the following apparatus, the one in the diagram, and we've also got a measuring cylinder, 100 centimeters cubed. We've got a stop clock and a balance. Right, outline how the student could carry out the experiments and explain how the results could be processed graphically. So I don't think you're going to have to, because they tell you basically what's happening there. So it's really the calculations this is about. So you're going to put the zinc into the flask immediately, and also put the hydrochloric acid in the flask first, and then drop the zinc in, put the bung in, and measure the volume of gas, say every 30 seconds. Every 30 seconds until it stops. That's what you're going to do. Now we need to talk about the amounts of stuff here, because it's asking us about calculations. So it's really about calculations. How much zinc, how much acid, and so forth. That's what we're going to have to calculate now. Okay, so we need an equation there. So zinc reacts with hydrochloric acid as shown. You're going to get zinc chloride and H2 gas. Right, so balance that to there. So it's quite important. We're going to need 2 moles of hydrochloric acid for every 1 mole of zinc, and for every 1 mole of zinc we're going to get 1 mole of hydrogen. Now what volume of hydrogen are we producing? 72 centimeters cubed. So let's work out the moles of hydrogen, and then from that we can work out how much zinc we're going to need. Moles H2 is equal to volume over 24,000. So that's 72 over 24,000. That works out to be 3 times 10 to the minus 3 moles. Okay, so how many moles of zinc are we going to need? We're going to need the same as that, 3 times 10 to the minus 3. We also, now it does say in the question, it says that it's going to use an excess of zinc. So this is going to be the very minimum amount of zinc that we should use, and we're obviously going to use a bit more. So let's say the minimum moles of zinc is going to be the same as that, 3 times 10 to the minus 3. The minimum mass of zinc is going to be moles multiplied by MR, the AR, sorry, of zinc. 3 times 10 to the minus 3 multiplied by zinc is 65.4. That gives us 0.1962 grams, and that's the minimum amount. So I'd suggest that we use, say, 0.3 grams approximately. As long as it's more than that, that's fine. Now let's think about the volume, or how much the HCl now. Okay, so how many moles of HCl are we going to need? Well, we've got 3 times 10 to the minus 3 moles of zinc, so we need to double that moles of HCl. So moles of HCl we're going to need is equal to 2 times 3 times 10 to the minus 3, which is equal to 6 times 10 to the minus 3. Right, now let's say what volume of HCl are we going to use? Well, let's say we've got 1 mole per decimeter cubed, concentration of 1 mole per decimeter cubed HCl. It's a fairly standard reagent you have in a lab. So let's work out the volume. So the volume is going to be equal to the moles divided by the concentration, which is equal to 6 times 10 to the minus 3 divided by 1, which is equal to 6 times 10 to the minus 3 dm cubed, which is equal to 6 centimeters cubed. Now, we were given a 100 centimeter cube measuring cylinder. Okay, so we can't measure out 6 centimeters cubed with a 100 centimeter cube measuring cylinder. It's not very accurate. So what I would suggest to use, instead of using acid of this concentration, which I originally suggested, let's make it 10 times weaker. So using 0.1 mole per decimeter cubed HCl, we will need not 6 centimeters cubed, measure out 60 centimeters cubed. Okay, so that's the amounts of stuff that we're going to use. Now it asks us to explain graphically how we would process our results. So remember we said we measure the volume every 30 seconds. So you're going to plot a graph here, and you're going to have time on this axis, and this is the volume of gas in centimeters cubed. Right, now you're going to end up with a curve which would look something like that when you plotted it. Okay, the reaction will slow down as the so the rate of reaction, of course, is the gradient of this line, and the reaction is slowing down as the acid is getting more and more dilute, it's getting used up. We want to find out the initial rate. So what we need to do is we need to draw a tangent at time 0. There's time 0 there. Draw a tangent to that line. And then we need to find out the gradient of that tangent. And that, of course, will give us, that's equal to the rate of reaction. The initial rate is the gradient at time 0. So then you probably don't need to say this, but there's your change in x. There's your change in y. Gradient is equal to the change in y over the change in x. Okay, so that is all you need to, and that is everything you need to say for that 6-mark question. Right. So we're now onto hydrocarbons. Okay, a student carries out an experiment to measure the enthalpy change of combustion of hexane. Now, what is the formula of hexane? Let's write that down. It's C6 and H2N plus 2, so it's H14 for hexane. Right, so we need to work out delta H, the enthalpy of combustion. How are we going to work that out? We're going to use the two following formula. We need to use Q is the quantity of heat released in the experiment, which is equal to M C delta T. M is the mass of the water that we're heating up in the can, which is 200 grams. C is the specific heat capacity of water, and delta T is the temperature change. Delta T, let's just work that out there. So 65.5 minus 20.5 is equal to 45 degrees C, 45.0 degrees C. Right, now once we worked out Q, then we have to convert that, that's the quantity of heat released in the experiment, convert that to a molar amount. So delta H is equal to Q divided by the number of moles of hexane that we've actually burnt. Okay, right, so let's work out the moles of hexane that we've burnt there. Right, with the MR of that, the molar mass is 6 times 12 plus 14 gives us 86. Okay, so moles of hexane is equal to the mass over the MR. The mass we have got is 1.29 grams divided by 86, which gives us 0.015 moles, okay? Okay, so we're ready to put the numbers into the blue equation here and the green equation later on, okay, here. Right, let's do Q first of all, the quantity of heat released in the experiment. Now this is 200 grams. That's very important that you use that mass there, and people will make a mistake and use that mass, which of course is completely wrong because it's the mass of water that you're heating up in the can, okay? So that's 200 multiplied by a specific heat capacity of water, multiplied by 45, and that gives us a value of 37,620. Okay, joules. Now let's put that into the green equation to work out delta H. So delta H is equal to Q, 37,620, divided by the number of moles, which you worked out over here, 0.015 moles of hexane. And that gives us 2.508 times 10 to the 6 joules. Now, appropriate number of significant figures. Well, we should give it to 3 significant figures because all of our data, every bit of data there is given to 3 sig figs. Okay, so I'm going to convert it into kilojoules as well. So first of all, let's convert to kilojoules. So we've got to divide by 1,000. So that's going to be equal to 2,508 kilojoules. Now we've got to remember that that is a minus there because the temperature is the temperature went up. It's an exothermic reaction, so don't forget a minus or you lose a mark for that. So that's the 4 significant figures. So to 2 significant figures, that's 2,510 kilojoules per mole. That is our value for delta H combustion. Okay, the calculated value for hexane in this experiment is different from the data book, where it's always much smaller or less negative, mainly because a lot of the heat is lost to the surrounding. It doesn't all transfer to the water in the copper can. It loses the surroundings. And another possible reason where you get less energy is because you get incomplete combustion. When hexane burns, you probably get quite a smoky flame, showing you're getting some carbon there. You're not getting it all going to carbon dioxide, and that of course will reduce the amount of energy that you'll get. So the 2 main reasons there. Okay, data book values for standard enthalpy of combustion of the first 4 alkanes are shown in the table. Methane, ethane. Okay, so you've got that. The first 3 are plotted on the graph, and you've got to plot the value for butane. Right, so what we need to do is we need to, well, look at the graph here. It's got relative molecular mass, sorry, on the axis here. So what's the formula of butane? Well, it's C4. How many H's? H2N plus 2, so H10. So the MR of butane is 58. Okay, the MR is 58, and so we need to plot that point, minus 277 and at 58, which is that red point I've plotted there. I did it earlier. Okay, and those points form almost exactly on a perfect straight line. So draw a straight line with a ruler there. Use the graph to estimate the energy release during complete combustion of 1.8 grams of pentane. Okay. Well, we need to measure out what's the enthalpy of combustion of pentane first of all. So delta HC pentane. Right, now pentane is C5H2N plus 2, 12. Okay, so the MR pentane is 72. So we need to get 72 there, which is quite hard on this. I think it's there. A bit easier on it in a book. Okay. I might be slightly out here because of the, okay, but you interpolate the graph like that. And that is, I think, delta HC is minus 3,600. Okay. Right, that's how much when you get, so if you burn 1 mole, you get 3,600 kilojoules out. Now we need to work out how much we get for the amount of moles we've burnt, which is a we burnt 1.8 grams. So let's work out. So what we need to do is the heat released, let's call it Q, like we did in the last one. Q is equal to delta H multiplied by the moles. Okay, how many moles of pentane have we got? Let's work that out first. Put it down here. Moles C5H12 is equal to mass over mR is equal to 1.8 over 72, we said, yeah, which is equal to 0.025. So Q, the heat released, is going to be equal to delta H, 3,600, multiplied by 0.025, and that's equal to 90. Okay, and the units are going to be kilojoules, so it's about 90 kilojoules. Right. Now here is a question. I've got to use Hess's law. The equation for the complete combustion of cyclohexane, it's not hexane, it's cyclohexane, that's that formula, is shown below. Okay, that's the equation. Standard enthalpy chains of formation are shown, and we've got to use them to calculate the value for delta HC. Now, when you're given delta HF values, and you draw a Hess's law cycle, we should put elements in their standard states at the bottom here. There's the third thing. So I'm going to put 6 carbons, solid, plus 6 H2 gas, plus 9 O2 gas for oxygen. Now, formation, we're forming these things, so the arrows are going to go up. We're going to form hexane from its elements, and we're going to form carbon dioxide and water from its elements there. Okay, so let's put the numbers on here. Well, what we're doing on the red arrow, we're just forming 1 mole of hexane, so that is just minus 156.3. The green arrow, well, we're forming 6 moles of carbon dioxide, so it's 6 times that number. We're forming 6 moles of water, so 6 times minus 285.8. Add all that up together, you get minus 4075.8. Now let's work out delta HC, which is this arrow here. Now delta HC, well, we're going against the red arrow, so we change this sign, so that becomes plus 156.3, and we're going with this green arrow, so that remains as minus 4075.8, and if you work that out, you get minus 3919.5 kilojoules per mole. That is the enthalpy of combustion of cyclohexane. Now, that is as far as I'm going to go with that paper, and I'm going to continue with the second half of the paper in the next video.